Okay, I think we can start now. So, welcome everyone. Today we are very excited to have Dr. Khullar with us. He is a bound postdoctoral fellow at the University of Washington for Innovative Astronomy. He got a PhD in 2022 from University of Chicago and Cobley Institute for Cosmological Physics. Today, his talk is titled Catching Galaxies, Napping with JWST. So please join me in welcoming Dr. Khullar.
Thank you so much. I really appreciate you all for having me here. Aurora seems like it's doing some awesome work, and I'm very excited to be participating in this. Let me just set up my slides and make sure that I can see you all as best as there is a way to go. Sorry, I'm just struggling a little bit here. One second. On my end, I'm just trying to see how to also enable gallery view alongside. I think I know what to do. Right. You all still see my screen, yes? With the fancy Galaxy cluster.
Yep. Yes.
Awesome. Okay. Let's go for this. Awesome. So my name is Gourav Khullar. My pronouns are he, him, his. And I am a postdoc fellow at the University of Washington. I've been working here for the last year and a half. A lot of my work over the last few years has focused on the question of quenching. And thanks to magical telescopes up in space, that question has led me to the first galaxies. And what I'm going to be talking to you about today is a combination of sort of this two-pronged approach that I've been taking to solving uh, of trying to solve the question of why the first galaxies we are seeing in the universe have quenched, and what could be behind this very sometimes niche, sometimes common population of post-starburst galaxies that we're finding above redshift 2. So these are colloquially called nappers. I'm going to be talking about this in a lot of detail. And this title slide just want to highlight a few teams that I've been working with. I'm helping lead. Um, so I'm happy to answer questions about the organizations as well that I'm sort of displaying here. But let's dive right into sort of the story that I want to tell you all today, which is uh, very much related to the timeline of the universe we were able to access before and after JWST. So here I'm showing sort of roughly the access that we had before JWST in units of redshift or years after the Big Bang. We could only go up to redshift 4, redshift 5 spectroscopically, and that too only for bright star-forming galaxies that allow us to see things like Lyman alpha C4 emission from space. Hubble Spitzer did a lot of lifting there. But the spectroscopically, the redshift 5 and above universe was a tricky one especially to build a substantial population of galaxies. And the reason why that is something that is exciting to me is because I think galaxy mass growth is a pretty awesome question to think about. And the way I like to think about is in the context of a parameter space that looks something like this, the star forming main sequence. So this is an XKCD-fied plot of SFR on the y-axis as a function of stellar mass, which is x-axis. And this parameter space has historically, at least for the last 20 years or so, allowed us to really, really nicely divide populations on the basis of their specific star formation rate, the ratio of the y over x. The main sequence is where most of the galaxies sit, as most of you may be aware. A lot of galaxies sit in the starburst region. They form a ton of stars relative to their stellar mass. They're probably going through an episode while we are observing them. Galaxies like the Milky Way are these transition galaxies hanging out in the Green Valley zone. And then there are my favorite galaxies, the red and dead ones, quenched systems. So when I say quiescent, post-starburst, these are all systems that have had a star forming episode in the past or multiple star forming episodes in the past, and now are in a state of quiescence, either for a long time or just recently. The critical issue that still remains is, of course, that we actually don't know the pathways that galaxies definitively take to go from the main sequence to quenched. And that's sort of one of the most exciting questions to me, especially in the early universe, where we think that star formation is quite stochastic and bursty. Sort of the transition from being a main sequence galaxy, or even if the main sequence existed at that epoch, is something that's an open question. But I'm excited about the question of like how do things become quenched, regardless of where it is in cosmic time. Again, pre-JWST, the very general, I would say, like a first order picture that formed for quenching is as follows. Star formation is approximately happening at all radii within the galaxy. Most observations of baryons in a population of galaxies has shown us that as of the pre-JWST era. Then what happens is we form these high central high central stellar mass density cores that, because of gravitational collapse, consume the core molecular gas quite rapidly and form these quenched cores, and then that quenching sort of proceeds inside out. And by redshift 0, you see a typical Milky Way type, almost quenched galaxy or very quenched galaxy. This is what we approximately think used to happen. So around redshift 2 is where we started seeing these quenched cores in galaxies, thanks to Hubble observations. And so I thought most we used to think that most of this picture is under control until interesting things started happening with JWST. But to first order, quenching happens because of two reasons, in my opinion, and I think in the field's opinion. Star formation needs cold molecular gas, and that too a steady supply of that. And quenching happens because either the gas flow is getting interrupted, or gas is getting heated. The things that were going to form stars don't form stars because something happens that causes the core gas to heat up and not gravitationally collapse. And so this is a beautiful schematic from a paper in 2019 by Allison Mann and Ciriobelli that basically summarizes sort of the big picture aspect of what happens when gas is inflowing into a region and may or may not form stars. And so, gas may not accrete because of external factors. Gas that is about to cool does not cool because of things like AGN feedback, supernova feedback, gravitational and shock heating. Cold gas is not forming stars, even though it's cold enough to traditionally form stars. Again, because of AGN feedback, morphological quenching, et cetera, we can talk about these things for days, right? Or cold gas is just rapidly consumed and the supply is not enough to catch up with the demand of cold molecular gas because there is some sort of positive AGN feedback happening, et cetera. So this is sort of the physics, and the way we are trying to understand sort of the motion of things that are happening is, of course, in units of whether quenching is happening slow or fast, or it's happening in a secular way, which we're calling mass quenching, or it's environmental effects, so we're calling that environmental quenching. These are some of the terms that you would see in quenching papers, as some of you may be familiar with, that are coming up a lot. These are concepts that allow us to understand what may be happening in a given galaxy or a population of galaxies. But now we come to my favorite part, which is pre-JWST. We've known stuff to redshift 6, 7, and now suddenly we, with JWST, have access to a very different part of the universe during and before and at the beginning of the reionization period. So we're really, truly looking at the first galaxies, both imaging-wise and, more importantly, spectroscopically. And of course, JWST, one of the most magical things humans have created, is doing amazing in terms of both discovery space, but also detailed observations and follow-up studies way. I like the Eagle Nebula picture. That's why I show it. I mean, I'm mostly a high Z person, so I actually don't know much about the Eagle Nebula. I mean, especially what's happened since the JWST observations. So if anybody in the room knows more about that, please let me know. Um, so just a general picture of what JWST has done for quenching or for mass assembly studies. Initially, it broke things. We found that galaxies seem to be forming massive stellar populations much earlier and much faster. And a lot of that had to do with this fundamental question: do we know how to measure stellar mass of things that we're seeing in the high Z universe? A lot of these massive things turned out to be little red dots because our mass to light ratio conversion, instead of being attributed, the light being attributed to black holes or black hole shell stars, was being attributed to galaxies, which is why these high luminosity objects seem like high mass galaxies. So this problem of measuring stellar mass appropriately is partially solved, and we know what to do the rest of the way to solve this. The other question that I'm also, I think, deeply entrenched in is, are early universe quench systems going to stay quenched? And we are finding a lot of them. These are some of the spectroscopic studies that are happening through systematic and one-off surveys, where we are finding, again, these unique exotic galaxies with giant Balmer breaks, which is this blanket absorption of lines blueward of 3650 angstroms that are traditionally seen in galaxies where younger stellar populations like O and B stars have sort of evaporated, and it's only the old stars that are left. These Balmer absorption features like H gamma, H beta, H alpha are things that we are seeing as well. And I think what's interesting here is that even with weak emission lines, we do think that most of the star formation stopped happening in a lot of these massive quench galaxies, at least a few hundred million years before the epoch of observation. So in short, redshift 3 through 7 universe has shown a ton of massive quench systems. And please keep an eye out for the words I'm using. Keep an ear out for the words I'm using. Massive, I think, is critical here. Traditionally, we feel that the larger the dark matter halo that these galaxies are residing in, the most likely that some of these stellar populations are much more evolved. So young stars have died off. So we do think that some of these massive quench systems are not going to start forming stars again organically or secularly. Maybe they will go through environmental things like mergers that will allow them to acquire more molecular gas and then later form stars, perhaps. But we don't know the future. What we do know is that these old stellar populations seem to be like in a very evolved state. So in short, bunch of quench systems above redshift 3 and 4. But how do we go about finding them with photometric and spectroscopic observations? And this is where interesting techniques like spectroscopic follow-up and stellar population synthesis modeling come in, which is my bread and butter. My objective as a cog in this wheel is to translate observations that we see of these galaxies into physical processes, or at least properties of stellar populations in galaxies. And so approximately the way we want to do that is we want to map these emission, absorption, slopes, normalized values of the flux densities that we are receiving from these objects into properties like age, metallicity, and dust. And so this is a really basic sort of flux density figure from Leisure et al. 2017, where we're showing rest frame wavelength on the x-axis, flux density on the y-axis. And you can clearly see that young stellar populations, 0 to 100 million years, have a bunch of emission lines. They don't show any Balmer break. As we go older to 300 million year, 1,000 million year, 6,000 million years, a lot of these emission lines that are characteristic of young star regions that are these hot ionized nebulae, those all disappear, and all that's left is really red spectra that have things like 4,000 angstrom break or Balmer break. So things like the UV continuum usually show us a star formation rate averaged over 100 million years. The H alpha emission usually is a very good indicator that star formation has recently happened, so about 10 to 20 million years, depending on who you ask. And then we've got the Balmer break, which is 200 to 500 million years. And so like these are the sort of interesting things that, interesting spectral signatures that we are really on the lookout for when trying to connect stellar population properties to photometry or spectroscopic observations. And the biggest part about sort of this methodology and actually doing it is the process of theorizing these light that we theorizing these photons that we're receiving um, um, from these galaxies into sort of stellar components, dust components, and gas, right? And that's essentially what stellar population synthesis is. Us assuming that a galaxy is just made of dust, stars, and gas, and we are successfully somehow able to attribute the light that we're getting from them into these discrete components. And the way we do that is by assuming things like dust laws, metallicity, evolution, and one of the biggest components of SPS modeling or SED fitting that some of you may be familiar with is how do we go about assuming the star formation history or star formation rate as a function of time for a given galaxy. So if you have, here are some examples that I'm showing about on the right is the star formation history model. If you assume it's a constant model, then the flux density on the left could look something like a combination of absorption features from old stars and emission lines, because the old stars there was star formation in the older part of the galaxy's lifetime. If you have rising or bursty star formation, you see more emission lines. If you see quenching, then the emission lines sort of disappear. But there is a fundamental issue. And the issue is that parametric star formation histories, which fundamentally assume a functional form, can cause a little bit of a problem. And sort of the problems are related to the fact that the physical quantity that we are interested in is things like mass-weighted age or the quenching epoch. But the issue in Bayesian analyses that we traditionally do using various statistical methods are placing priors and conditions on the parameters of these models that are not necessarily the physics that we want to get out of them. So as an example, what I'm showing with arrows for 5 versions of functional or parametric star formation histories, these arrows are mass-weighted ages for all of these things. But the mass-weighted age is not what you put a prior on. And what that is leading to is, unfortunately, biased priors even before you have provided your model with any data. So if you're doing a delay tau model, which is of the form x times e to the minus x, you have a prior typically that is linear in x. But the prior that's linear in x is not linear in mass-weighted age or quenching time, or time since quenching or quenching timescales, or burst timescales, which are the physics properties that you're interested in. And this leads to all sorts of problems. On top of that, functional forms are not flexible, which means that if you, on the x-axis, each row here is basically an input model, and each column is a model that's fit to those inputs. And you can see that a lot of these models seem to be quite constrained in terms of trying to reproduce the shape of these quirky star formation histories. So like the models that you're seeing, our best fit models are in black, the posteriors are in gray. I hope this figure is convincing you that none of the models can constrain bursty star formation or quenched star formation. And that is a major problem. And therefore, the goal is to move towards more flexible star formation histories, which we are calling non-parametric star formation histories in the field. And sort of this is where the field is moving at the moment, especially everybody who's doing stellar population synthesis modeling over the last 10 years is aggressively moving in a direction where more flexible or non-parametric star formation histories are able to reproduce many different shapes of intrinsic or true star formation histories. So I've thrown a lot at you in terms of the methodology. Are there questions that I can answer before moving on to the next part here, where I show you flashy JWST observations?
I think we're good.
Awesome. Awesome. There are no questions? Yeah, just confirming. Okay.
Yeah.
Awesome. Cool. So one of the ways in which I have helped contribute to sort of this story is that some of these non-parametric star formation histories are not able to capture recent bursts and stochasticity. So what you want to be able to do is be able to capture the most recent bursts of star formation history without predefining these age bins that allow us to flexibly model weird wiggles or stochastic star formation and quenching episodes. And so what I've done is I've used a form of non-parametric star formation history first devised by Rensis and team in 2022, where the oldest stellar populations, which is on the left here, so t equals 0 is the Big Bang, t universe is the redshift of the observation. The oldest bins are something you predefine, they're super broad. And then this intermediate range of bins are actually calculated on the fly. These are bins of equal stellar mass formation, which means that if you see a burst, suddenly see a really thin bin that the Bayesian analysis is actually calculating for you. And that allows you to basically reproduce a post-starburst galaxy quite efficiently. And what I'm doing is I'm trying to incorporate a photometric redshift component in this, which means that the x-axis is not fixed. The x-axis is also being explored at the same time. And this is amazing for the rich tapestry of photometric SEDs that we have at our disposal with JWST. This is an example of a redshift. This is a redshift 3.3 galaxy, where you can clearly see that a flexible star formation history on the right is doing a really good job of constraining both the photometric redshift because of this Balmer break you're seeing, as well as old stars, intermediate stars, and low recent star formation. And that's sort of this joint SED fitting using this flexible star formation histories as well as the redshift is allowing you to simultaneously constrain all these properties and basically discover a family of quench systems above redshift 3, which is what I've done for the Uncover survey, which is a deep survey of the lensing field Abel 2744, where we've discovered about 70,000 different galaxies photometrically. But photometry is awesome. Don't get me wrong. Photometry is great. I'm a spectroscopist by trade because spectroscopy, again, allows you to deal with a lot of the issues that I've been describing. Things like the age metallicity dust degeneracy, things like photometric redshift characterization, which might lead you into weird corners of parameter spaces because an emission line might be confused with Balmer break, or a Lyman break at 1200 angstroms could be confused with a Balmer break. This means that the properties you're getting for the galaxy are completely different from what they actually are, which is why we need spectroscopic follow-up. Not to mention that the star formation history constraints are much tighter. So what the field has done is a very good job of finding some of these high redshift systems, but something weird has happened. And this is sort of where the story gets interesting. This spectrum I'm showing you on the left is from a paper by Tobias Loser et al. 2023, where they found a quench system at redshift 7, the first one ever. Redshift 7 is when the universe is 800 million years old. Actually, no, it's lower than that. I'm being wrong there. I think it's like 600 maybe. Please, the cosmologists in the room, please, I apologize if this is wrong. But too early to form quench systems. I think let's go with that. And what they're finding with NIRSpec, which is the near infrared spectrograph on JWST, they use the PRISM mode, which is a low resolution mode with amazing sensitivity and wide wavelength coverage that allows them to simultaneously measure where my cursor here is, the Lyman alpha emission and break. In this case, there is no emission. And of course, the Balmer break. And their models suggest that there are a bunch of concurrent Balmer absorption features, including lack of H beta, and subsequent observations have shown there's no H alpha either, which means that the star formation history looks something like this. The galaxies formed a bunch of old stars, but the most recent burst of star formation happened 100 million years ago, and it quenched 20 million years ago. And this type of post-starburst galaxies, which in colloquial terms is now being called mini-quenched systems, B-type post-starburst systems, this population is growing in number. And I think this is one of the most exciting things to do at the moment. Are these just antecedents of massive quench systems? Are these a new class of post-starburst systems that just happen to be in this early universe because we just have so many galaxies there? Or are they this component or a subpopulation of the broader star formation history framework at high redshift galaxies, where galaxies form starbursts and quench temporarily, and they starburst again and quench temporarily. Is there an ebbing, flowing way of forming stars, which we are calling stochastic star formation history, that these post-starburst galaxies are part of? That story, or the answer to that question, is not definitive yet. And I hope to contribute to that a little bit, which is, are we actually directly probing stochastic star formation history just in a lull phase? Which is why one of the things that we've done is call them nappers, because they might wake up at any time. And so to connect this a little bit more to what we think is happening, the hypothesis is that a mini-quenched galaxy is doing something like an episodic quenching. And so there is some stochasticity in the availability of gas or the star forming efficiency, which means the galaxy may have the gas it needs to form stars, but something is going on that is temporarily causing an inefficient star formation. And so if you look on the right, this is the classic classic galaxy regulator model proposed by Simon Lilly et al. In 2013, where gas inflow into halos and eventually into galaxies, and then ongoing star formation is creating this variable gas reservoir. And any star formation is basically based on whether this variable gas reservoir can very easily convert to stars, which we term star formation efficiency. But there might be outflows at play. There might be AGN feedback at play that is heating the gas up, again, episodically, that might be leading to stochasticity in star formation. We are quite a bit away from unpacking this in detail for these high redshift systems. And hopefully I'll be able to convince you why in a second. In simulations, the way folks are trying to find these quench systems or these galaxies in lull phase, I'm going to call them nappers from now, are basically finding galaxies that are stochastically moving about the main sequence. So on the top left is the same plot that I showed at the beginning of the talk. And what we are basically finding in some of these simulations like Vela is a bunch of these systems that if they were caught in the starburst phase, we would see a lot of emission lines in the spectra. But if they're caught in the lull phase, it is likely that that's what we're seeing in these post-starburst galaxy observations, the signatures of. One thing that I do want to flag here is that this ebbing and flowing seems to traditionally, it seems that folks are expecting that this happen traditionally in low mass galaxies. And that just is by virtue of the fact that low mass galaxies live in low mass halos. They can't hold onto the gas efficiently enough that would have otherwise formed stars. And this ebbing and flowing mode of star formation is because gas is escaping and then coming back again, escaping, coming back again, leading to inefficient star formation episodes. In a second, I will tell you why we don't like that approach by itself, because we're finding some interesting things in observations. So let's go back to the Uncover survey. It's a team that I've been part of over the last 2 years, where we have spectroscopically found a bunch of these systems between redshift 4 and 7. Hopefully, you'll see this paper on the archive in a month or so, where we are finding spectroscopic signatures of galaxies that have both young stars and old stellar populations, as well as our modeling is suggesting a recent star-forming burst. And the traditional shape that we're seeing is exactly what I showed to you in the redshift 7 galaxy before, which is that you see a Balmer break, you see a blue UV slope and a bright UV luminosity, and lack of emission lines or very weak emission lines. And that is a classic signature of what we're calling nappers or B-type post-starburst galaxies. And so we have found anywhere between 8 to 10, depending on exactly where the cutoff is. But spectroscopically, we know that these systems have H-alpha, weak H-alpha or no H-alpha, which means star formation has not happened in the last 10 to 30 million years. There's Balmer break, which means there are old stellar populations. And there's UV flux, which is telling us that there was star formation 100 million years ago. And so what you're seeing on the right is sort of my manifestation of the star formation main sequence, where these galaxies are sort of moving along the main sequence. So hopefully it's convincing you that what you're seeing in the cartoon figure on the left in red is sort of being emulated by these galaxies on the right, which is time averaged star formation rates. And so if you average 200 million year timescales, you see yellow points that seem to be star forming. And then if you see 10 million time squares, which are in dark maroon, they are sort of in the quenched region of the star forming main sequence, sort of hopefully convincing you that all of these systems seem to be going up and down the main sequence. If they're going to come back up is a question that is an open one, which I'm happy to postulate with you all. But our combination of photometric and spectroscopic studies have shown us that you need some version of spectroscopy, which you're seeing here in gray data. You need some version of spectroscopy to be able to model the star formation history accurately. And what you're seeing on the right in blue is the spectrophotometric reproduction of the star formation history. Medium band photometry, which we have from the Mega Science Survey, which is targeting the same field, Able 2744. So at the moment, we have every single filter that JWST NearCam is allowing us, which basically is effectively an R of a 15 spectrum. So it's a very coarse spectrum, effectively. What this is showing is that imaging-only modeling sometimes can characterize both the burst epoch and timescales. This is, by the way, stellar population synthesis modeling using the code Prospector that maybe some of you may be familiar with. That's the one that I use. What this is also showing is that if you just have broadband photometry, which is spanning, half a micron or quarter micron, and not sampling enough spectral features that can constrain fun things, you can see on the right in yellow that you're not getting any quenching, you're not even getting any starbursty epoch. So what we are finding is that broadband photometric SEDs are not good for finding post-starburst or quenched galaxies at high redshifts. You need at least medium bands, and prism spectra, which are these low resolution spectra, are doing wonders. So yeah, that's sort of what we are finding at this point. So we are at the half-hour mark. I have a small other section that I would like to cover here, but are there any questions about the photometric and spectroscopic characterization that I've been part of in terms of nappers? All good?
I think we're all good.
Great. Please feel free to pause me at any time. I personally don't like when a lot of jargon terms are thrown consistently. So if I'm being unclear about something, I would love to dive deep into that. So what I've done so far is hopefully done a decent job of painting a picture that high redshift quench systems are a subfield in its own at the moment. And it's a beautiful place to be, both in terms of finding potentially permanently quenched systems that can tell us a little bit about like how galaxies stop forming stars as a function of cosmic time, but also these post-starbursty systems may have some interesting signatures to that we can isolate eventually, and maybe they are their own class of galaxies, or maybe not. I think we're a few years away from definitively answering that question, but I just want to be part of that journey. I think is sort of been my point. But what I've done is I've given you a picture of what we're finding in terms of populations of galaxies with global measurements, right? So I think just to be clear, all of these galaxies are, we put a slit on them, just one giant slit, and we modeled them as global systems because these are high redshift systems, and it's really tricky to unpack the constituent stellar populations of them unless we are treating them as an integrated blob effectively. But the fun part about all of this is that even though deep fields are doing a really good job of characterizing the integrated properties of galaxies, they're actually not probing the physical scales on which galaxies are built. And I'll tell you what I mean by that in a second. Again, another wonky thing of showing very near field images in a high Z talk. And I'll tell you why in a second. This is I think this might be my favorite image with JWST. This is the mid-infrared instrument that is probing 5 to 28 microns, a previously relatively unexplored part of the electromagnetic spectrum in terms of astrophysical objects. I think Herschel was one of the ones that allowed us to study this a little bit, but the mission was only for 2 years. So MIDI, when it shows these this NGC 628 observations through the FANG survey, you can clearly see this beautiful web of star formation, gas everywhere, and these red regions that are all stellar nurseries. Some of them are star clusters, some of them are open clusters, etc. And in the near field universe, we've done a really good job of sort of unpacking the physics of galaxies that we can spatially resolve. Like SDSS has an IFU program, MANGA, that has made things like H alpha emission. So really, literally showing you where the star formation has begun. D4000 maps that are showing you where the old stellar populations reside. But what I'm excited about is, can we do this kind of connection of stellar populations and gas that we do with robustness at redshift 0? Can we do that at cosmic noon and beyond? And that's because at redshift 0 with NGC systems and a combination of JWST and ALMA observations, we found that the global observations are not sampling where star formation is happening. This is an ALMA map of a redshift 0 galaxy where we are finding giant molecular clouds, which are literally where star formation begins. They're all at 100, 50, 200, 500 parsec scales. So if you're integrating these galaxies that are 2,000 parsecs, 3,000 parsecs at high redshifts, or even 1,000 parsecs, you're blending the signatures that are coming directly from the most star-forming regions. So we are not probing the spatial scales of star formation. And most importantly, we're not probing the spatial scales of quenching. And so what do we do? How do we find 200 parsec scale data? And the answer is lensing. The combination of lensing and JWST is a magical one that hopefully folks in this room are familiar with why it's magical. But just to give a quick primer, lensing is effectively an intermediate massive galaxy acting as a lens. It could be a group, it could be a cluster, and it's distorting and magnifying the image of a distant galaxy. And so at high redshifts, Hubble has kind of sort of shown us that if we can do lensing reconstruction, we can actually probe regions in these highly magnified arcs and resolve down to less than 10 parsec regions above redshift 2. And so I want to give you an example of how we're going on about this. This is the program that I'm leading from JWST Cycle 1 as part of the COOL-LAMPS program. I'm very, very happy to dive into the detail in the Q&A part of what this COOL-LAMPS thing is. But what we're finding is this is a redshift 5 galaxy that we thought was very star forming, but you can see the color differential in this RGB image from JWST, and we're calling it the WAS arc because of obvious regions. Sorry, I don't like flashing this for too much because Disney will sue us, whatever. But the WAS arc is, it turns out a 2 kiloparsec galaxy. I'm showing you the source plane reconstruction here. Made up of a few clumpy regions. Galaxies at high redshifts are quite clumpy. But the exciting thing about this galaxy where the magnification is happening such that we are seeing this 10 to 100 parsec clumps, like this is a 50 parsec, 75 parsec clump over there. This is actually a really red galaxy. And that's because it turns out it's very likely a napper. And we didn't know this before JWST because we thought it was just a massive star forming system. How do we know that? I just want to show you how we're going on about this. NearSpec also has an IFU component. It's one of the most amazing instruments there. This is work that is being led by Taylor Hutchison, who's a postdoc at NASA Goddard, and Brian Welch, who was at Goddard, but is now at the ISI Institute in Bern. Both of them are our resident NearSpec IFS experts, where they are mapping pixel-level spectra from this galaxy onto 1D spectra that then we can do stellar population synthesis modeling with. So it's a three-dimensional cube, effectively, with spatial and spectral information. And so this rich tapestry of data that we have at our disposal is really revealing some interesting things about galaxies like the WAS arc. So this is an example from the templates program where you're just basically walking through the wavelength slice of the cube. And this is a lens galaxy at redshift 1.3, and you can clearly see how the data quality is. But for the WAS arc, you're basically seeing a difference between strong, weak, and no emission regions. And if I was able to convince you of these globally quenched systems, you saw a lot of absorption and Balmer absorption lines in particular. And that's what we are seeing in this galaxy in detail. So much so that we're seeing presence of multiple flavors of old stars through these Balmer absorption and even metal absorption lines in some cases. And the best part about this galaxy is that it's very, very similar to low redshift, irregular post-starburst systems that through SDSS manga studies, we think were quenched because of merger or irregular or non-axisymmetric feedback through AGN or even supernovae. And so the exciting thing about this galaxy is this is just one system, but we are at the moment in a deep dive into sort of this IFS spectra. One of the papers led by Taylor Hutchison probing the nebular regions of this post-starburst galaxy is already out on arXiv. Please have a look. My paper will be out soon that is going to be leading sort of the star population analysis of this. So please keep an eye out for that. But this is one galaxy. I love single galaxy studies, but we do want to move in a direction where we can study star formation and star formation and quenching at high redshifts, and that's why we need a sample of lens systems. And this is where a program that I'm co-leading, it's the Cycle 2 program called the Legos Survey. I'm happy to dive into the story behind the logo. We're very proud of it. But basically, the idea is that we have a set of 8 galaxies with anywhere between 100 to 300 unique clumpy regions. And we're building a survey of clumps. And a lot of these clumps are star forming, but a lot of these clumps are also quenched. And so we're kind of taking galaxies apart and putting them back together. That's where the word Legos comes from. I know it's awesome, right? But this is the 8 galaxy sample. It's being led by a bunch of awesome folks. Just want to flag Matt Bayless and Michael Florian, who are fellow co-PIs with me. And again, Brian and Taylor are helping us sort of build the legacy data set that this is through the NearSpec IFS component. So each unique image that you're seeing here, so obviously these galaxies are multiply imaged because of the lensing and shearing effect. We've basically plopped JWST IFS observations on one unique image for each of these objects. And it turns out that one of these galaxies actually is a post-starburst galaxy that seems to be going through some sort of a merger. This is a redshift 3 system at 10 to the 10 solar masses. On the top, you can see there's a clear gap in the flux between these two clumpy components. And we think that this galaxy went through a merger. Stellar population synthesis modeling of one of the clumps sort of shows you the star formation history on the right. And if you make continuum H-alpha Balmer break maps, you see a huge distribution that looks something like this. This is a plot of individual clump region spectra in decreasing order of Balmer break strength, which means the oldest stars are sitting on the top, the youngest stars at the bottom. And so we're seeing a huge diversity of galaxies in here. And so we can't wait to share the beauty that is the Legos survey with you very, very soon. I'm very, very happy to answer questions on this. This is my summary slide. I am, as I said, trying to understand the question of quenching and the two-pronged approach is studying the integrated properties of these high redshift population of galaxies, but also a deep dive into some of these quenched lens systems. And I'm very, very happy to answer any questions. I know that you wanted me to talk a little bit about sort of my background, and I'm very happy to do that as well. I have a single slide, but I can dive into this during the Q&A part or however you all want to do this. But again, thank you so much for listening to me. I threw a lot at you all, so please ask questions. Thanks.
Thank you. Questions from the audience?
Thanks, Brian.
Yeah. He has to go teach now.
Okay, first of all, very, very nice logo. Let me there. That's my question. Okay, thank you for your nice talk. I have a question about, okay, I want to know your thoughts about these quiescent galaxies that we are finding in high redshift, that they are usually very blue in UV, and we have no emission lines in the optical, let's say that the Balmer lines that we like. So what do you, okay, and we talk about post-starburst galaxies, and you talked about reconstructing the star formation histories using STD modeling, prospectors, backpipes.
But we know that we have a problem with the attenuation models that we assume. So what
Yep.
do you think about like having these different attenuations? Because we study the integrated light and we do not know about the like how dust is spread throughout the galaxy. So what we don't see any emission line because of the attenuation.
Yeah, so that's an interesting question. So one, lensing will help you understand that a little bit better, right? Like the local dust maps. One of my PhD students at the University of Pittsburgh, who's part of the LEGOS program, is studying the WASARC, that individual system I showed you, and basically mapping the dust that is being produced by gas versus stars, and sort of really answering the question, like what is causing the lack of emission lines around the O2, H delta, H gamma region. So yes, you can build empirical dust attenuation laws, right, if you have enough wavelength coverage and enough data. But for these mapping systems and the post-starburst galaxy systems, like I really do think that ALMA data will help a lot in unpacking the connection between dust, metallicity, and age. The bright UV slopes and UV luminosity suggesting that there is not a lot of dust in some of these systems, but we might be missing dusty nappers. It's actually a question that I'm dealing with, like literally, like since the start of this year. Like, what is the population of nappers that we're missing in these high Z surveys? Are we missing the dusty ones? And the answer to that is not clear yet. But yes, you're right. The dust attenuation laws at high redshifts are a little bit wonky. A lot of people are working very hard on unpacking those. One of the ways that we're going on about this is looking at the steepest and the shallowest dust laws and then marginalizing our answers over that. That's an easy way out. But I'm all for more ALMA data on some of these systems, and then unpacking the sort of the thermal balance, the energy balance connection between dust attenuation and emission. But the fact that H alpha doesn't exist is a really strong indicator that there's no star formation in the last 20 million years. So recent quenching did happen.
Hi, can you hear me from here?
Yes, I think so.
Okay, so I wanted to ask more about the COOL-LAMPS program. I read that
Yes.
it started at an undergrad course-based research experience. So what made it work for so long?
Yeah. So this is one of the most amazing and fortunate things that I've been a part of. I'm one of the initial founders because it just happened to be the TA of the program when it started at U Chicago. COOL-LAMPS, which the name was by the way, if you see the logo, it's actually the WASARC, which was the flagship discovery of COOL-LAMPS. It's a stretch, but come on, it's fine, right? Like, so it stands for Chicago Optically Selected Lenses located at the margins of public surveys. The U Chicago, which was in the year of COVID, so we didn't know COVID was about to happen, but that was the first year where this new concept of classes came into play at U Chicago, because of work that was being done by the undergraduate college and most importantly the PI of the program, Professor Mike Ladders. Mike was my PhD advisor, and he's a galaxy clusters lensing expert, and has done a lot of work in the discovery space of finding high redshift systems. He wanted to lead a program that is very common, in fact, in paleontology and archaeology spaces, which is that classes, like undergraduate classes, in one quarter or one semester, do a lot of learning and pedagogy work to understand the field. They design a research program, and then during the breaks or during specific research periods, they actually go on a dig, and they actually do real science, and then they write a paper. And so this field course concept is actually built upon a framework called the CURE pedagogy framework. This is course-based undergraduate research experience. And the idea with COOL-LAMPS was to bring this to astronomy. Some similar programs do exist elsewhere, but this is very particular where in our quarter system, we make undergrads spend one quarter learning about galaxies, clusters, and how to find lenses. And then we use Magellan, which U Chicago has access for. The whole class is centered around Magellan observations, both photometric and spectroscopic. And the exciting thing about this was that we basically got to use the big telescope, and then students got to write papers. The first version, which was the was art paper, was led by me. I just happened to be the TA at the beginning. And for me, which it's really important that any sort of pedagogy and teaching conversations include tried and tested inclusive pedagogy methods. And so this Cure class, this field course class, really became a really nice sandbox to test out some of these individualized self-instructor evaluation stuff, engagement opportunities based on not what Mike wants or I wanted, but what the students wanted. How do we navigate this tension between a classroom and it's actually a collaboration, right? So it's very much more informal in terms of pedagogical requirements. There were no assignments. Everybody got an A if you were genuinely excited about the work. So a lot of those things were tested in this framework. And the most exciting part is that over the last 5 years, there have been 5 iterations of this class. I was involved in the first 2 iterations before I graduated, before I got my PhD. And we've written about 10 papers, most of them led by undergraduate and graduate students. And so COOL-LAMPS is amazing. And I'm sure that if there are faculty in the room, they've definitely received a lot of applications for grad school programs from COOL-LAMPS students. There have been about, 55 undergraduates who have gotten their primary research experience through COOL-LAMPS and gone on to do super awesome things in astronomy and beyond. I'm very proud of this program. And so just to give you the scientific context really quickly, because I went on the pedagogy side, we're literally discovering objects that are photometrically publicly available in decals, pan-stars, and LELV data. So it's GRIZ photometry, but specifically in the margins of the distribution of source color and brightness. And so we've done visual examinations of 1.1, 1.2 million lines of sight. I've myself done about 300,000, actually looked at images. It's really fun, I promise. And of course, like this process allows you to build a parent sample, then you use other analytical techniques to build a short list, and then you go on Magellan and observe things. Yeah, that's COOL-LAMPS.
Amazing, thank you.
Yeah, of course. Sorry, I have some extra slides. So yeah, are there other questions? I'm happy to give my spiel here if you like. Yeah, and I know there are only 7 minutes left, but I'm happy to stay for 10, 15 minutes longer if people want to chat more. I just want to say, like, mine has been a not that unconventional, but a little bit wonky journey. Hopefully you can tell that I didn't grow up in the US. I grew up in India, and in 2010, when I'm really old. In 2010, when I started my undergraduate studies, astronomy in India was not supported pedagogically as much. And so through mentors and conversations I had with folks who had the experience, they felt that engineering schools offered you a better shot at understanding what astronomy PhDs look like, rather than astronomy or physics degrees. And they were right. I'm glad I listened to them. So I went to an engineering degree. I went to the Indian Institute of Technology, Delhi, and did a degree called engineering physics. My particular concentration of that 4-year B.Tech program was lots of optics, which was really fun, lots of semiconductor science, which was not fun. And so I did a lot of optics courses as electives because that's where I felt like I could learn about telescopes and things. But I think that 4-year degree really gave me a really good opportunity to understand what the landscape of research looks like, got me REU opportunities I otherwise would not have. So I was very fortunate to be participating in that engineering community. I led clubs and things like that. So that was really fun. Again, is the only reason I feel like I had visibility. I was one of those people that you may have heard that do this. I'm sure you all have received these emails. Every summer, people write 200 emails, 300 emails to ask for REU opportunities. That's what I did for 2 summers. And, out of the 200 people who I wrote to, 5 responded. And then luckily, one of them every summer said, okay, you can come work with me. that's how I grew my network, because India at that time did not have any optical and infrared astronomy connections. That was the reality 15 years ago. So I did an exchange program in Erasmus where I did some radio astronomy stuff, and then I spent a year at Cambridge, which was great from an astronomy perspective. Got me to my U Chicago grad position, but it was very intense. And Cambridge is a bubble for folks who've not been there. It was not my kind of place at all. Hopefully, this is exactly what you're looking for. I'm also happy to go in a different direction. For grad school, sorry.
This is great. Thank you.
Okay, cool. For grad school, I went to U Chicago, as I mentioned, but I started very late, which is to say that my first couple of years were not a great experience. I worked with a couple of different projects around galaxy cluster optical observations with the telescopes, but with also with sort of theoretical models around clustering and dark energy survey, etc. I ended up continuing my work with clusters, which happened to have these beautiful lenses. So my PhD ended up being a clusters plus lensing PhD, but I actually changed my advisors to Mike after my second year. So I was always very behind my peers who were already going to conferences by the time I started writing a single word in Overleaf. And that's just because I think that I just did not have a good fit. I think that grad school, as I'm sure a lot of you have experienced, can be a very challenging place. And I realized that if I didn't have an advisor who treated me as a human being, it was going to be really hard for me to spend, whatever number of years I would spend doing this. And then, I luckily got to go to a bunch of telescope observations. Chile is an amazing place, and thankfully not rife with sort of land disputes and protests. So I consciously feel it's a good place to go do astronomy. The COOL-LAMPS program was such a happenstance, just happened to fall in my lap, and I just took it because I love working with students. And now I still do COOL-LAMPS stuff, but I use the Apache Point Observatory because University of Washington has access to that. So I'm looking at, I'm still doing COOL-LAMPS science, but with a different telescope. And so, yeah, that was super fantastic. And my first postdoc was great as well, where I started really leaning into my JWST side of things. And again, it was a very different network. So it was a lot of beauty in matching what my advisor was teaching me with what my postdoc advisor was teaching me. So it was pretty exciting. And yeah, that landed me here at University of Washington, where I'm pretending to be a faculty by running a small research group because I have so much data and so many fun ideas that I want everybody to work on those. So I have a graduate student here and 2 undergrads who are doing some kick-ass science around lensing and JWST based on Legos and whatnot. So I'm happy to dive into any of these aspects, any questions that you all have. I know we are at time, but again, I'm very happy to stay until 15 past to talk. But yeah, thoughts, questions, concerns?
Okay, I have a question. I'm
Please.
curious about the part that you mentioned that being in Pittsburgh for your first postdoc taught you how to think outside of the box. What do you mean?
Yeah. So I think so my postdoc was a wonky one because because it was a fellowship. A lot of postdocs, even if they're not fellowships, even if they're associate positions, allow you to be very independent researchers these days because everybody wants to show that in faculty applications. And my advisor was super awesome. I worked with Professor Rachel Bazanson. And I think one of the things that I learned was one, how to juggle multiple projects, how to reserve time and focus, which I'm still struggling with, and I'm much better than I was 3 years ago. One of the things that was very exciting was just be really creative with projects. Most of the things that I'm working on now came about because of what I learned in the first year of my postdoc. This job came about when I was in the first year of my postdoc. The one that I'm in right now, I'm in. So there are 5 or 6 different ways in which I felt like the creativity would not have existed if I didn't have the set of mentors I had, especially Rachel. and I didn't have the two different networks that I'm talking about. This lensing cluster network that I had for my PhD, and the new postdoc network of this high Z galaxy field that I built with Rachel and team. So I think what I did in my postdoc that is exciting is I could try to connect these two worlds, and that's how I was able to basically hire a PhD student at UPET who's still there, Julissa Sarmiento. Julissa is the one who's working on writing a paper this year to unpack the connection between dust around gas and dust around stars in these lens galaxies. Um, and Rachel is the co-advisor, and she's the co-advisor because that's a question that she's excited about now too, thanks to the fact that I convinced folks to be creative and connect different worlds and projects together. So yeah, there are lots of ways in which I feel like I'm much more creative now than I was, um, and just don't want to do the conventional postdoc way, which is you work on one project at a time. I'll be very honest, I get bored very quickly, so that was never going to be me. Um, does that answer your question? I don't know.
Yes,
Yeah.
thank you so much.
That's great. Especially for job market.
Something specific, I think.
I think we shall adjourn.
Okay, last questions about megascience.
No, ask as many questions as you want. No problem at all.
So you said that with megascience, with medium band photometry, we may use these like downturns in star formation rate. So how good are the medium band photometries in like not in downturns? I'm like, how good are they in capturing the star formation history in general?
Yeah, that's a very good question. Let me see if I have extra slides that show this. Probably not. Sec. So out of the 8 galaxies that are in my almost submittable paper draft, half of them have medium bands that let me get the upturn and downturn pretty decently. A lot of it depends on whether you can sample H alpha, whether you can sample Balmer break, whether the medium bands are allowing you to constrain the photometric redshift appropriately by constraining the Balmer break. It's a combination of factors that's leading, and like, is the medium band deep enough to get both the blue and the red side of the Balmer break? So it's a combination of factors that is letting me decide whether a medium band distribution, which is every single medium band with NearCam, can let me constrain Napper or post-starburst properties at redshift 5 or something. Because if you think about it, like redshift 5 may let you sample the key things, but what if it's redshift 5.2 and the spectral features fall off the filter? And then you can basically fit anything in filter edges, right? And that's what we are seeing in a lot of these galaxies, that we cannot distinguish between a purely star-forming galaxy versus something that had a burst and a quenching episode. If the H alpha, for example, just happens to sit between two filters. So it's a complicated question. It's a complex question, but I think it's a really good one.
Thank you so much.
Of course. Any other questions you all have in terms of career trajectory, wonky things?
Do you expect yourself to be on the market for a professor position somewhere? Since now
Yes. This fall is the one. So 6 months from now, I will be on the market for faculty. It's unlikely I'll be applying by myself. My partner is a professor here at the University of Washington, so we'll both be applying together.
I see.
At Riverside, I don't know. Do you have near field cosmologists? Like people who do like dwarf galaxies, stellar streams, that kind of stuff?
No, we are. Yeah, we have simulation people who care about that, and but we don't have an observer here that do this near field cosmology stuff.
I see. Yeah, my partner is Professor Nora Shipp. She's faculty here. So yeah, we both will be applying in the fall. Well, if Riverside has openings, let us know. We would love to bring JWST and Rubin science. That's what Nora works on. That's also what I'm working on, to find new lenses, just like COOL-LAMPs, but using machine learning methodologies to find lensed arcs in galaxy clusters with Rubin. University of Washington is a Rubin hub, so we're doing a lot of work in that direction.
Awesome.
Thank you so much
Yeah.
for your time.
Thank you so
Of
much.
course. Thank
Yeah.
you so much for having me. I really appreciate it. Yeah, please let me know if there are any other questions that you all have and anything that I can answer. Yeah, no, anything about, grad postdoc organizing or teaching or stuff like that. I have a little bit of experience in a few of these things, so yeah, please let me know.
Cool. Well, bye.
Awesome. It was great meeting you all, and I hope you all have a restful weekend.
Thank you, you too.